The next thing for us to talk about is primes. So this is really a new section. And what I want to do is I want to talk about everything that we know about primes, and then we'll get into some of the nitty-gritty as we have time. But an integer n greater than or equal to 1 is prime if the only divisors, the only positive divisors of n are 1 and n. Notice that 1 is not a prime. 1 is also, so if an integer is not a prime, it's called composite. So an integer n greater than or equal to 2 is composite if it is not prime. And therefore, it's a binary condition for all integers 2 or greater. You're either prime or you're not. Okay, so these are the important definitions here. So prime and composite. Notice that n equals 1 is not prime and not composite. So it's neither prime nor composite. And there's good reasons for that, which we'll get into. So as far as the primes go, the primes include 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43. We could go on and on. And in fact, one of the first things that we'll prove, and maybe one of the second things that we'll prove, is that there's infinitely many primes. Okay, which sounds kind of obvious maybe, but there's not, right away without thinking about this too carefully, we can't conclude that there's infinitely many primes. Maybe there's some conspiracy where all primes have to be no more than a billion or something. Of course, that turns out to be false, but this is something that deserves a proof. Before we can do that, we have to talk about the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic basically says that primes are the building blocks of the positive integers. So this says let n be greater than or equal to 2, then n is either a prime or a product of primes in a unique way. So, or a product of primes in a unique way. When I say in a unique way, what I mean is that excluding the fact that multiplication is commutative. So excluding the reordering of the primes. So what I mean by this is that if you were to pick any number, say 30, 30 is either prime or a product of primes in a unique way, in this case 2 times 3 times 5. And this is the only way that you can write 30 as a product of primes, with the exception of the 6, you can write it as 3 times 2 times 5, or 3 times 5 times 2. I don't care about the reordering. So those don't count as different. So the uniqueness is that this is the only set of primes that we can write 30 as a product of. So 30 is 2 times 3 times 5. Okay, so the uniqueness is in that set of primes. The proof is by strong induction. Okay, so the proof is by strong induction. We don't need more than one base case. So our base case is just n equals 2, which is prime, and we're done. That's literally all we have to do for the base case, because the statement holds for n equals 2. For the inductive step, we need, so for our inductive step, what we're going to do is we're going to assume that the statement, all integers how do I want to say this? All integers j so all integers j such that 2 is less than or equal to j is less than or equal to k are either prime or a product of unique primes, let me say it that way because that makes it sound like I'm saying unique meaning distinct, which I don't mean, but it's a product of primes in a unique way. So we're assuming that the statement's true for all values j up to some k. So in a unique way, for some k greater than or equal to our last base case. And then our goal is we want to show that this statement is true also for n plus 1. Am I doing that? No, for k plus 1, because that's the way I have this written. So we want to show our goal. I think this is just important to keep in mind. We want to show that k plus 1 is either prime or a product of primes in a unique way. Okay, so classic induction, assume that it's true for all values up to k. We want to show that it's also true for k plus 1. Okay, so our product of primes in a unique way. All right, there's going to be 2 cases. So this is a nice example of a strong induction proof. We have, like I said, strong induction. We're going to have 2 cases. If k plus 1 is prime, then we're done. So if k plus 1 is prime, then the conclusion is true. Then the statement is true. Okay, so if k plus 1 is prime, we're done. If k plus 1 is not prime, in other words, if k plus 1 is composite, that means that it's not prime, and therefore there are integers. I should have explicitly said this up above. Primes are the integers whose only factors are 1 in itself. If that's not true, the integer is called composite. So what that means is that you can say n is composite if there exist integers a and b. We can write n as a times b, where a and b are both between 1 and n. Okay, so between 1 and n. So if k plus 1 is composite, then there exist integers a and b, so that k plus 1 is equal to a times b, where a and b are at least 2, and at most k. Let me be consistent. So less than k plus 1. And I could write it like this, or you could write it as a and b are greater than or equal to 2, but less than or equal to k. Now, by our inductive hypothesis, remember that we assumed that the statement was true for all values up to k. Well, a and b are less than or equal to k. So by our inductive hypothesis, a and b are either prime or they are a product of primes in a unique way. And hence, so is their product. So k plus 1 is also a product of primes in a unique way. Okay. What I want to do is, and that's it. So that's our proof. And so I have 2 comments on our statement, on our proof here. The first is this statement, this fundamental theorem of arithmetic, explains why 1 is not prime. If 1 was prime, then what you could do is you could take any prime decomposition of a number and add 1 to it or remove 1, and then you lose the uniqueness. So if one was a prime, then these would be two different ways of writing 30 as a product of primes. So that's why we say one's not a prime, so that this statement is true. The second thing is, why did we need strong induction? Why was weak induction not enough? And so if you think about it, this has a lot to do with if you take 1001, and I should pick another number here that's a little bit easier, but if you take 1001 and you want to determine whether or not 1001 is a prime or not, it turns out that it's not. I need a calculator here. 1001 is a multiple of 13. I just need to think about what's that multiple, and it turns out that it is 13 times 77. So it's 13 times 11 times 7. Usually you write the primes in increasing order, but this is the order that I wrote them in. So 1001 is a product of primes in a unique way. That has absolutely nothing to do with the fact that 1000 is also a product of primes in a unique way. So increasing a value by 1 does not tell you anything about its prime decomposition at all. So 1001 is, of course, 2 cubed times 5 cubed. It's 10 cubed. So 2 cubed times 5 cubed. And so adding 1 to this value, okay, so adding 1 completely changes the prime decomposition that you have. So there's no mechanism for weak induction to work. There's nothing that the factorization of k tells you that'll be helpful with determining the prime factorization of k plus 1. Okay, so that's why we needed strong induction, is that we needed to assume things about all the values less than or equal to 1000, not just 1000. Okay, so just a little insight there on why we need strong induction rather than weak induction.